Welcome. My name is Ron Papa Schmidt, and I'm the creator of the Net Zero Now YouTube channel. This is going to be video 10C, high and low pressure systems, and this is going to be an overview. It's going to be the one of many videos I'm going to do with regard to high and low pressure systems. In this particular video, the first thing I'm going to do is I'm going to do an overview of the basic science. So how do high and low pressure systems really operate? Why do they function the way they do? And then we're going to go into the three major types of high pressure systems: thermal, dynamic, and hybrid. So let's begin. Yeah, I'm recording this in late March of 2026. And I just thought this was an appropriate way to start, because we really find ourselves in a unique situation right now. And that is, with climate change, who do you believe? I mean, we have politicians and special interest groups that are telling us daily climate change is a hoax, it's a con job, it's a scam, etc. And then we have the climate scientists and their data. And if you take a look at the right-hand side, what are they telling us on the top? They're telling us temperatures are increasing at an accelerating rate, and they're increasing fastest in the Arctic. And then if you take a look at the diagram below that, the heat map below that, you'll see that if you look at it carefully, you'll see at the pole that we've increased basically 4 degrees Celsius, which is equivalent to about 7 degrees Fahrenheit, in the last 50 years. So what's happened is the temperature differential between the pole and the equator has shrunk dramatically. And so what does that mean? Well, here's what the climate scientists are telling us is going to happen. They're telling us right now we're basically on the Titanic. We're moving full speed ahead for the iceberg. And what they said, we're at 1.5 degrees Celsius to 59.2 degrees Fahrenheit at the end of 2024. And they said when that occurs, you would see significant environmental, economic, and social impacts. And I think if you've seen the weather in 2025 since then, I think you would have to say, and so far in 2026, you'd have to say, yeah, I think there has been some significant changes here. It is having an impact on us. Now, what they're also telling us is that in the last 10 years, between 2014 and 2024, basically we went up a half degree Celsius. So they're saying, what if we just follow that forward, that says we're at 2 degrees Celsius about 2034. What they're telling us is going to happen is the world will see catastrophic and likely irreversible damage at that point in time. And if you see the weather trends that are going on right now, etc., you say, maybe that looks like that might be believable. I don't know. But they're telling us that 3%, that would be another 20 years from there, so about 2055, 2054 or so, basically we'd be living in a nightmare scenario. And if you carry that out another 20 years, it basically says the world is a planet unrecognizable to human beings. It's something we've never, ever experienced. So the question you have to ask as you look at this video, well, who do I believe? And so I want you to do, the reason I put this up in front, I want you to think as you're going through here, because we're going to talk about how high and low pressure systems work. And what you're going to find is that everything is pretty much interrelated and substantially influenced by temperature differentials or absolute temperature levels. And I think you can see sort of the integration that happens within our environment and the resulting conditions we have on Earth. And so I want you to think about this as we're going through this presentation. Are the climate scientists right? And then ask yourself another question. Have you ever seen anybody who's a climate denier ever talk about this stuff? So just keep an open mind as we go through this. So let's begin. So let's start with the real basics here, okay? sort of what's a definition of high and low pressure system? Okay, what's the definition here? So atmospheric pressure, what is it? It's the weight of a column of air pressed down by gravity at a specific point on Earth's surface. That's pretty easy to understand, okay? And so what does that tell us? Air pressure is highest at sea level, and it decreases as you go higher. So the higher you go, the less air pressure you have. Okay, so how do you measure air pressure? Well, they really do it in two ways. They do it in millibars and inches of mercury. So is there a common denominator? Yes. So what happens is that the Earth's surface is not flat, right? We have large mountains and valleys, etc., and things like that. And so if we take the air pressure at any one point in time, we're going to find there's always going to be a difference associated with height. So what they do is they've gone through the process of basically converting everything to sea level. And when they do that, they have sort of a standard air pressure they can measure that against. So with the air pressure, if we do it in millibars, it would be 1,013.25 millibars would sort of be average air pressure. And if we did it in terms of inches of mercury, it would be 29.92. And with the common denominators, when we talk about air pressure any place on the planet, it's always sort of converted down to Earth, to sea level, so we can always compare them to see what's going on. And then the last thing that's sort of important here is that cold air is denser than warm air. And so they took the average height of 500 millibars of air pressure, with just average temperature would be sort of in the middle there. But you can see by the illustration on the right, if it's cold, it's lower. If it's warm, it's higher. Well, why is that? Okay, it's because as air warms up, there's energy that causes air molecules to move faster. They collide more aggressively and spread further apart, and therefore there's more height to warmer air than there is to colder air. Now let's go to the next sort of fundamental thing when you talk about air pressure. And these are two sort of concepts of air movement. One is convection and the other one is equilibrium. So convection, we can sort of, maybe I'll just walk through that by looking at the illustration on the right here. What happens is that the sun sort of sends energy down to Earth, which heats the Earth's surfaces. It's called radiation. And so as the Earth's surfaces then warms, what it does, it warms the air above it, which then in turn results in convection, or the air rises into the atmosphere. So that's basically what's happening. That's sort of the concept of convection. And then what happens as it gets higher into the atmosphere, it cools down, and then it comes back, it becomes heavier and comes back down to Earth's surfaces. Again, we complete that cycle over and over again. Now, the other important concept to talk about here is equilibrium in terms of air movement. And basically, nature always seeks equilibrium. And what that means, air quantity. Okay, so high pressure has a surplus of air or more air than low pressure does, which has a deficit. And so what happens is that naturally then air flows always from high pressure systems to low pressure systems. Now the other question is, does Earth ever get the equilibrium? It never does. Why? Because we're rotating. And the second thing is we're getting a constant input of solar energy. So now let's get to the next concept. And this is high and low pressure systems, and sort of how do they form? Okay, so high pressure systems form when cool, dense air sinks from the upper atmosphere towards the ground. It sort of piles up on the surface, and then it sort of pushes out. If you take a look at the illustration here, and you look at the blue cylinder of high pressure, you can see that. The air comes down because it's pressed down. Then as it gets heavier and heavier, it sort of pushes out at the bottom. Now, how does that impact our weather? Well, because the air is coming down, clouds cannot form, and so we end up with clear skies and sort of calm weather in high pressure areas. So what happens with low pressure? Well, the low pressure area basically is just the opposite. So it forms when air rises. And as air moves up, what happens, it then sort of spreads out. And what it does is sort of pulls in the air from, it's almost like a vacuum, if you want to call it that, pulling in the cold air from heavy air from the high pressure system. Now you see above the cylinder in the right hand side there, you see rain clouds. Well, why is that? Well, as the warm air rises, if it has moisture in it, it condenses into clouds and eventually into rainstorms and precipitation and other kinds of things, thunderstorms and all kinds of things. So that's how those systems form. Now, the next question is, well, how do they behave? They basically rotate. And if you take a look, maybe to start with looking at the diagram in the upper right-hand corner, rather. If you see the high pressure system there, that's the larger circle. What happens is that as the air comes down, it sort of rotates to the right, as you can see, or it rotates clockwise, and then it sort of feeds air to the low pressure system, which in turn rises up, and it moves counterclockwise, in a counterclockwise direction. So why is that? So let's talk about that. Maybe before I get into that, let me just cover one other thing here. If you look below that map, you also see in the southern hemisphere, and you see those, that's just exactly reversed. In the southern hemisphere, the high pressure system moves in a counterclockwise fashion, and the low pressure system moves clockwise. Now, if you take a look at the map directly below that, I sort of identified the areas in the northern hemisphere between the equator and 60 degrees latitude. And if you take a look across that, you see massive amounts of brown space. That's land. And basically, they estimate somewhere between the high 80s to up to 90% of the world's population lives in the northern hemisphere between the equator and 60 degrees latitude. And so as a result of that, outside of this slide, I'm only going to talk about the northern hemisphere. I'm not going to mention on each slide that, okay, the northern hemisphere goes this way, but in the southern hemisphere, everything's going to be reversed. First of all, since 90% of the people live in the northern hemisphere, I think it just simplifies the presentation. So just assume I'm talking about the northern hemisphere every time. I'm not going to continue to mention that. So let's go from here to what happens. So what causes that, those rotation differences? Think of a merry-go-round. You have the center of the merry-go-round, you have the outer edge, right? And the outer edge is moving much faster than the center is. That's called a speed gap. The same thing applies to the Earth. So if you look at the Earth's equator, it's about 24,000 miles long, and the Earth spins roughly at about 1,000 miles an hour at the equator, because we have a day lasts 24 hours. And near the pole, we're spinning at about zero, well, not quite zero, but closer to zero, okay? So what happens is that we also know from previous presentations that air always moves from the equator towards the poles, right? So as it starts that movement, it sort of moved to the east. Why is it moved to the east? Well, that's because that's the way the Earth is spinning, from west to east. And so as it's moving, the air in the upper atmosphere isn't moving as fast as the air on the ground. And so it sort of outruns it, if you want to do that. And when that happens, it just turns to the right. Now let's get the high and low pressure system. So a high pressure system, what's happening? Think of it as coming in the center, air is coming down and going out. You can also think of it maybe as a fountain where water's coming down and rolling out. So if you're at the fountain looking out, what happens is that as the water is going out, it turns to the right. Well, what way is it going? It's going clockwise in the northern hemisphere. In the southern hemisphere, this is reversed, okay? That's the last time I'm going to mention that, by the way. Now let's take a look at it from a low pressure system. So what's happening in a low pressure system is that water's coming from the exterior and sort of moving towards the center. And so what happens with that is it turns to the right. Now, to give you an example, let's take a look at a roundabout, right? No matter which direction you're coming into the roundabout, whether it's north, south, east, or west, you're always turning to the right. And which way you're going? You're going in a counterclockwise direction. So that's why high pressure systems move the way they do in the northern hemisphere, and low pressure systems move counterclockwise the way they do. So let's move on now. So now that we've talked about high and low pressure systems, how do they fit into Earth's atmospheric circulation? Well, first of all, Earth's atmospheric circulation, it's sort of really, if you could think about it, it's sort of a massive heat redistribution engine that follows sort of the following hierarchy. First of all, you have these planetary infrastructure systems. These are sort of the broad pressure systems that are driven by the Earth's rotation, the Coriolis effect, and the fact that air moves from the equator towards the pole. And so really you have four major areas: ITC, Hadley cell, Ferrel cells, polar cells. I talked about that in other presentations, and I'll talk about that in just a second here. And then you have temporary weather systems. And these systems are caused by the fact that the Earth is rotating, it's spinning around the sun. So we have seasons, there's mountains, there's oceans. So these global belts sometimes get broken up, and sometimes they turn into moving high and low pressure systems that create our local weather. And they can be broken into three fundamental categories: thermal systems, dynamic systems, and hybrid systems. Thermal systems are formed by surface temperature differences in the Earth, whether it's land or water, and sometimes between the two of those. And they provide the fuel for a lot of our daily weather systems. Dynamic systems are really created by the movement of air in the atmosphere, by convergence and divergence, and the Earth's rotation. And they sort of think about them as providing sort of the spark that turns thermal energy into hybrid daily weather systems. And then we have the hybrid, which are sort of our daily weather systems for the most part. This is really sort of a combination of sort of the dynamic triggers and thermal fuel that create active moving systems that produce our day-to-day weather. So that's how that breaks down. So let me cover quickly the planetary systems. Now I've already done a whole 2 videos on this that sort of explain how this works. So I'm just going to go through this real quickly. The first is 10A and 10B, which would be atmospheric circulation, part 1 and part 2. And basically what you see here on this diagram, if you take a look at number 1, the Hadley cell, you'll notice that well, first maybe start better at the equator. So the equator is that yellow line. It's really called the Intertropical Convergence Zone, or the ITCZ, also the thermal equator. It's a low pressure system. It's at the Earth. That's where we get the maximum amount of sun rays, etc., which causes the Earth to warm fastest there and rise the highest. And you'll notice that if you take a look at this diagram as we get to the Hadley cell, you'll see that the troposphere, and that's that sort of light purplish area above the Earth, and you can see how it sort of shrinks as you get to the pole. That's because it's warm air is higher, okay? And we've already covered that previously. And so what happens, you have this massive high pressure system there. So what the air goes up, and then it starts moving towards the pole, or moving towards the cold area. As it gets cold enough, it sinks down at about 30 degrees latitude. That would be the horse latitude. That's the second yellow area there. And then it becomes a high pressure system. Now, if you take a look at just above that, you see the red arrow there. So what happens in high pressure systems is the air spreads out and goes towards in this case, it goes 2 directions. It goes towards the pole and towards the equator again. So as it goes to both of those other areas, when it gets to the equator, it warms up enough again, it goes back up into the air, into the low pressure system. And the same thing would be true at about 60 degrees latitude, or the polar front. That's another low pressure system, and you can notice that the air goes up there, then it heads towards the pole, the final version of that. So that's real quickly how this system sort of works. Now, there's one other important thing that we covered in those presentations I want you to know. And what we're heavily influenced by the fact that the Earth is tilted and it rotates around the sun. And so in the course of a year. And so as it does that, because we're tilted, different parts of the Earth get more sunlight at certain times of the year. And that sort of affects temperatures and things like that. So if you move over to the right-hand graph, you can see this is the ITCZ. So what you saw in the previous diagram as the ITCZ looked like a straight line, right? Well, it's really not a straight line. And it also doesn't stay steady. It moves. It moves in response to temperatures. And all of these systems move in response to the ITCZ. And so if you take a look at that, you can see from the blue line there, that would be in January, where the ITCZ, and then you can see as we move to summer, we end up with the pink line. You can see it's much higher in most cases. And you can also see it's not a straight line. It sort of curves. What causes that is you have temperature differences between land and water. And you can also see it's not the same thickness. It can be up to about 500 miles wide, and as it sort of moves up and down as we go through the seasons. That in turn causes everything else, the Hadley cell, the polar cell, all those things to move in conjunction with that. So that is a quick, or maybe not so quick as I think about it, high-level overview of the basic science associated with pressure systems. So now we're going to get in the first specific type of pressure systems called thermal high and low pressure systems. So let's do that. Now, so what's a thermal pressure system? So the definition is a thermal pressure system are atmospheric patterns that are primarily generated by the heating and cooling of air near the Earth's surface and are classified by the following categories. Their scale. Planetary ones. We've talked about the planetary systems already, and you can see how they existed and how they are influenced by temperature on Earth, like the ITCZ, etc. And then the next category would be synoptic. Those are sort of really long, large area of things. And again, basically 1,000 kilometers or more. And then you get into mesoscale, which is under 1,000, maybe up to 10 kilometers. And then you can go, from a couple of feet to maybe 9 miles or so for microscale systems. So like a mesoscale thing could be, maybe a mesoscale thing could be, maybe a synoptic thing could be a massive squall line. A mesosystem could be, I guess maybe probably, a synoptic system could be a massive front. Maybe a squall line would be a mesosystem, and then a thunderstorm or a tornado or other things could be microsystems. And so that's sort of how this works. But in this presentation, we're only going to cover the synoptic ones, okay? But other categories are surface types, so whether it's formed over land, which is called continental marine, or over ice or snow. They have vertical identification. Some are shallow, some are very deep, some are warm core, some are cold core, and that has an influence on it, on their behavior. And then they can be geographic forcing. Some of them are influenced by orographic, or by mountains and valleys, or what latitude it's at, or by coastal, land and water interfaces. Now I'm going to be doing a deep dive into just thermal pressure systems, so we're not going to cover any of that stuff for the rest of this presentation. But I just want to let you know that that's how they think about these kinds of systems. So let's talk about thermal low pressure systems, or synoptic systems. And so thermal synoptic low pressure systems are basically driven by intense solar heating of land masses, which causes air to rise rapidly. They're relatively shallow. They may only go 1 to 3 miles up. And unlike frontal systems, these typically remain stationary over arid land during the summer months. Now, if we take a look at it, the United States fundamentally has two large systems. One is the Arizona-Sonora southwest heat low. And this one actually give you a sense of the importance. This sort of can drive the North American monsoon season. And then we have the Great Plains heat low, which can trigger it's sort of responsible for triggering sort of tornado alley, where we get our severe thunderstorms and tornadoes, etc., in the central and southeastern part of the United States. Now, here's the strange thing about this, okay, and this is why I wanted to go over that and why this map is there. So this low system exists over a desert. If you remember in just the previous section, we talked about how, well, when you have low pressure system, what happens as the air goes up, if there's moisture available, it turns into rain, etc. So why are these systems over deserts, if lows cause rain? Well, what really happens is that for the Sonora Dennis, for example, if you take a look at the map up above where we have the latitude levels, you'll notice that the Sonora and Mojave Desert basically are subtropical hot deserts. They're at approximately 25 to 30 degrees latitude north. That means they're at the high pressure area that we have for the Hadley cell. And so what happens here, you have this low pressure area that is, because the land's so hot, the air starts rising. But it only goes up about, it's shallow. It only goes up, 1, 2, 3, 4 miles or something like that. And then it sort of slows down as the air cools. And what also holds it down is you have this massive high pressure system above it. And that high pressure system, because there's no moisture, also sort of prevents it getting up higher, drawing in more moisture to sort of cause rain or precipitation to occur in this areas. The Great Plains one, this is sort of a mid-latitude one. Now this one should be generating rain. The difference here is it's near what they call a rain shadow. It's on the other side, lee side of the mountain. And the lee side of the mountain, there is basically no moisture because all the moisture gets on the windward side of the mountain, where the wind direction's coming. As it moves up in the air, the rain is pulled out. As it moves over the mountain, there's basically no moisture there. And that's why this occurs at a different latitude, between 30 and 48 degrees, or in the mid-latitude areas. And you can see that from looking at the map up above. Now, we'll do the same thing now for the rest of the world. And there are basically 6 major thermal lows around the world. Now, most of these you'll see, like the Saharan low, and let me tell you why that's important, is this sort of triggers African easterly jets, which sort of are the seed for hurricanes. Or you can have the South Asian low, which is over the Thar Desert, and this sort of is a primary driver for Asian monsoons. I'm not going to, in the interest of time, I'm not going to go over that for each, what the primary drivers are for the rest of them here. If you're really interested, you could pause this slide and read that material. The other thing, though, that's kind of interesting, again, with the Sahara, so here we have another case where this low is forming over the desert. And you can see it's they call it a subtropical hot desert. And so because it's dry there, the warm air of the desert arid area sort of rises, but it's also reinforced by a high pressure system above it, because it's in the horse latitude area where we have these global high pressure systems. And so that's why you have low pressure systems forming over deserts, and why we have low pressure systems that generally generate a lot of precipitation do not generate precipitation in the case of these major thermal lows, synoptic scale thermal lows, I could say, around the world. And sort of the same thing's true for the Indian Desert, the Arabian Peninsula low, the Australian heat low. If you really want to get into each one of these you stop the thing, look at the video, but you'll see the same general kind of message that's occurring here. Except for the last one, let me just go over that. There's going to be a desert heat low, and this is in the northern plateaus of China and Mongolia. And again, this one's in the mid-latitudes, but it's again behind mountain range. So it's basically a rain shadow kind of desert, okay? So that's at the mid-latitude area, so that's why it's a little bit different than some of the other ones. Okay, so now let's talk about what is the typical weather pattern from lows. Well, generally, they form over large land masses like deserts during the summertime, and they heat up rapidly. And because the air is less dense, it rises from the surface. But the air is generally dry, and because in a lot of cases they have these high pressure systems around them or rain shadows, that you really don't get much moisture. Occasionally you'll get some, and when you do, you'll get some pop-up storms. But these systems also eventually drag in moisture from the oceans and water around them, that basically eventually then create the seasonal monsoons. And that occurs sometimes as these systems sort of move in conjunction with the ITCZ as it moves in different seasons during the year. And then you have cyclonic winds, which really basically means that they really move in a counterclockwise fashion in the northern hemisphere. So let's get to high pressure systems. And again, there's only two of these in the United States again. One is the Arctic Canadian high. And these systems, I guess I didn't read the definition up above, but these form generally over extremely cold and often cold and ice-covered sort of areas. And the cold, dense air sinks and creates these high pressure systems. Thermal lows are mostly regional, the ones we talked about just previously, but the thermal highs are almost continental in scale. And the two that sort of affect the United States, one is the Arctic Canadian high, and this massive in the northern Canada Arctic area, but sometimes it's such a dominant area, these Arctic outbreaks that we get, where we get this cold weather coming into the United States, centrally the United States, it really comes from this particular source. And again, if you were to look at the map on the other degrees, this is sort of at 60 to 90 degrees. And the reason it's called a polar desert, and the reason is it's so cold up there, there's really basically, it's very dry. So there's no moisture in the air. And then we have the Great Basin High. In this one, you can see an illustration of that on the right. This basically causes the Santa Ana winds in California as the winds move from the high to the low pressure systems off the coast of California. And again, it's seasonal because of the movement of the ITCZ as these systems move in response to the seasons. And this would be a classic Great Basin desert sort of a thing over this, and it's influenced, it's sort of a rain shadow again, influenced by the Sierra Nevada mountains, okay? And that's why it forms, because it's sort of in the mid-latitude. And now across the globe, we're not going to get into location of these because it's all pretty obvious. On an international basis, there are basically four. The Antarctic and the Arctic one, which is self-evident. The Greenland one, I want to talk about that for just a second because you frequently hear about that influencing our local weather. So this thing sort of forms over the extreme localized cold of the Greenland ice cap, okay? And it sort of acts like a boulder in the stream, if you think about it. Sort of, when a boulder in a stream, water goes around it, right? Well, the same thing's true with the jet stream here, and this sort of diverts the jet stream around it. And when that happens, it frequently then pushes this sort of Arctic air deep into the eastern United States, or in some cases, Western Europe. And so this can lead to sort of prolonged cold and snow. So you can see how this high pressure system in Greenland sort of affects weather in the United States. I'm just trying to point you out how all these things are interlinked. And and then we go to the Tibetan Plateau. This is sort of the third pole. It's also extremely cold in the and this sort of also impacts the Asian winter monsoons as they occur. And this system can really cause massive snowfalls in parts of southern China. Now, so how do high pressure systems really affect our weather? Often high pressure, they typically bring cold, dry, clear weather. These systems are opposed to thermal lows in that they are driven by the intense cooling of the Earth's surface rather than heating, okay? And so how do these synaptic systems affect our weather? One, they bring intense cold. Since they form over these large cold masses in winter, such as Siberian High, Kenyan High, they sort of provide the cold air that then eventually piles up and can eventually then be moved to our areas. They generally create into other areas of the Earth. They create clear skies and sort of calm winds. The temperatures are generally extreme. Because the pressure is so high, they're basically, it's sort of like it applies a blanket over the air. And so you end up with record-breaking low temperatures and fronts and things, the frost and stuff like that. You have air stagnation and fog. One of the other things, because it traps air near the surface, if you're in valleys, a lot of times you can get ground fog or the buildup of pollution and smog and things like that. And again, in the northern hemisphere, they move counterclockwise. Now, one other couple of things I want to just cover real quickly here and just show you the linkage, okay? Because remember, highs move to lows. So let's take the Arctic Canadian high and show that it moves to the Great Plains heat low. So it takes air, it moves it into that, or you can say the Great Plains pulls it, and this sort of triggers severe storms and cold wedges that happen under hot air. Again, we'll cover this when we get to the deep dive in the thermal system. I just want to show you, though, that there are these linkages. And then in addition to that, the same thing with regard to thermal high pressure systems. Here are the linkages here. So we take the Arctic Canadian high. It is sort of linked to, it has linkages, okay? So in this case, it's linked to the polar jet, and it basically takes it and moves it, and that's what causes sort of these outbreaks that occur when we get this extreme weather conditions in the United States. So basically, you can look at it as it provides the fuel, and then you have these other sort of planetary or hybrid systems that sort of can take that fuel and bring it to other parts of our area of the planet to present our weather patterns. And we have thermal low pressure systems. They also have linkages. For example, the Great Plains low here it has a dry line. This supercell storms come from that. And it sort of acts as a pump that takes Gulf moisture, which then in turn creates our tornado alley. So that was thermal systems. Again, we went over that very quickly. We covered a lot of material. So basically, we'll do deep dives into that to explain that in more detail. Now let's go over real quickly dynamic systems. And so dynamic systems, unlike thermal systems, are driven by surface temperatures. That are driven by surface temperatures. Dynamic systems are sort of driven by the movement of air in the upper atmosphere. And specifically, that's normally the jet stream and the Coriolis effect. And then we have sort of pure dynamic systems. And what happens in a pure system is the pressure is created only by motion and force. It's sort of like a fan, if you think about it. And so what happens is that anytime you're in the atmosphere, air is always being heated and cooled. And so they sort of naturally create these thermal pressure systems. But to get a pure dynamic system, you need so much force that it just overrides temperature. And there's only 3 of these that basically exists on the planet. One is the stratospheric polar vortex. I had a separate presentation where we talked about that already, so I'm not going to cover that here. Next is cutoff lows, and this is occasionally, in a jet stream, what will happen is that a pocket of air will sort of mechanically get pinched off from the jet stream and create its own sort of isolated weather system. And then you can have upper level ridges. That's high in the atmosphere. In the upper atmosphere, air currents can just pile up in that atmosphere and basically create a dynamic pressure system aloft, okay? But dynamic systems really have another role, and this is probably the major component of that, and we'll call that the dynamic component. And the dynamic component sort of acts like an engine that makes hybrid systems so powerful. Sort of think of thermal systems sort of piling up like the wood, and then what you have with the dynamic system is sort of a match and sort of a fan that keeps the fire roaring, is maybe the example. And so what you really have is it sort of acts like a trigger. So in hybrid systems, you'll have like a massive storm, which really starts with a thermal difference, okay? And then what happens, the dynamic force comes in, maybe a ripple in the jet stream, that starts it spinning. And so that spinning sort of creates a structure. It could be a cyclone, typically. And so as that spinning is going on, the dynamic movement sort of provides the mechanical force that holds that system together, so the system can hold together while it's moving across the world, okay? And then you have a multiplier effect. This is almost like can also act like almost a turbocharger to a pure system, okay? So what it does is the spinning physically it packs the air. And that dynamic part of the weather sort of like as a pump, and pumps the air much faster than simply heating or cooling would. So this sort of provides the engine for hurricanes or other kinds of things like that we have. So dynamic component is very important. So that's dynamic pressure systems real quickly. The real power now becomes through the hybrid systems. And so what are hybrid systems? Hybrid systems are semi-permanent, or they can be transient in nature. They originate by the interaction between thermal conditions, heating and cooling, and atmospheric dynamics, which is generally the jet stream and planetary rotation. And there are three major categories. There's migratory ones, or the travelers. These are the weather makers. I'm only going to talk about the ones that operate at a synaptic scale. Excuse me, it's been a long presentation, and I'm having trouble talking, apparently. And they're driven by the jet stream, okay? And then we have seasonal ones, which are sort of large-scale patterns that persist for an entire season. Then you have topographical ones, where you have obstacles, like where the weather patterns are created or permanently altered by Earth features like mountains and valleys and things like that. So let's talk quickly about each one of those. So the travelers, these are the ones that are driven by the jet stream. They are transient pressure systems, and those are the ones you see if you live in the United States. You see, those are the ones we get most exposed to in the mid-latitudes, okay? These are the local, so we have a local thermal factor. You have some heating or cooling going on. Then you have a dynamic factor, the jet stream that sort of takes these things along. And because they're migratory in nature, we're going to discuss this one like a process or a sequence of events, unlike the thermal ones, which are sort of stationary, okay? And so let's start at the beginning of this thing. So you have an upper level trough, or the setup. This is sort of where the storms begin, okay? So what happens, you have a ripple or dip in the jet stream, and that sort of acts as the architect, sort of deciding where the weather will change and where the storm will be steered. So this is sort of starts the initial storm moving. And there's a couple ways this happens. One is long waves or Rossby waves. We talked about that before. These are the big patterns. And then you have short waves, sort of kinks or something that can occur that can trigger, sort of a rainy day or short-term events. The next thing is then you typically have a frontal boundaries or you have a conflict, okay? And the concept here is, so what does this do? So the trough moves, it drags cold and warm air together into each other. This creates sort of clashes that create clouds and wind and signal sort of the beginning of a storm. So you hear about, an example of this would be warm fronts and cold fronts and dry lines. And then what happens, you have extratropical cyclones that are created. This is where the action occurs. And this is where the conflict of the front starts to spin, and this creating the actual weather event we experience. For example, would be nor'easters or Alberta clippers or polar lows, etc. And then you have the migratory highs. So after the storm passes, then what happens is the next thing that happens is you have sort of the high pressure system that comes in. And so you have heavy sort of stable air moves behind the storm, clearing the clouds, which sort of brings generally a pretty sharp drop in temperature. And you can think of Arctic outbreaks as that, post-frontal clearings or subsistence zones. Now let's get into the second one, the seasonal systems. And these think of sort of like the rhythm. So they're driven by the Earth's tilt and the way the land and ocean heat up differently, okay? And if a migratory system is sort of like an individual vehicle, these seasonal systems are sort of like the permanent highway that sort of dictate where these vehicles sort of go. And so the first major type is the monsoon systems. And so what happens? During the summer, the heat heats up faster than the ocean, and so sucks in this moisture, which creates then months of rain. And in winter, the reverse thing kinds of happens. The air blows out to sea, and you have dry area. And you have there's a couple of monsoons, the South Asian monsoon or the North American monsoons. And I have a separate presentation on monsoons that we'll also be talking about. So we're just going over this real quickly. Then you have sort of semi-permanent highs and lows. Think of these almost like guardrails in the atmosphere. They don't move much, so they force the migratory storms like nor'easters to sort of curve around them. This would be the Bermuda High or the Aleutian Low. Then you have the ITTZ sort of belt. This is the belt where you have massive amounts of constant thunderstorms going on. And this is where the traits winds meet. And it migrates sort of north and south with the movement of the sun. And so this can then bring wetter, drier seasons to parts of the tropics. And the last thing you have is teleconnectors or oscillations. And this is, they sort of shift the position of the jet stream for an entire winter. And they sort of can make the world either warm and other parts place cold. These are sort of massive switches that can occur. Think about El Nino and La Nina as an example of this. Those aren't annual ones, but they go through phases, sometimes a year and a half, 2 years or more. They go through a El Nino to neutral to La Nina and have a massive effect on our weather. Same things with Arctic oscillations. And again, we'll do separate presentations on each one of those so you understand how that works. And then finally here, to keep this moving along, we have the topographical ones. And these are weather patterns that are created by permanently altered by the Earth's features of the Earth, okay? And so you have, first type you have is orthographic lifting or rain shadows, okay? And this is when the moisture hits the mountain. This forces cool air up, which causes rainfall on the windward side, and on the leeward side, it causes dry and warm conditions. And if you go to the state of Washington, you notice on the west side of the mountains is sort of you have sort of high desert on the western side. I take that back, just reverse. On the western side, you have sort of lush greenery and forests, etc. On the eastern side, you have the deserts. The next type you have valley and gap winds. These are sort of funnels. This is sort of when air is forced between narrow gaps and mountain passes or down long valleys. It speeds up significantly. Examples would be the Santa Ana winds would be an example of that. Then you have lees and trough and mountain waves. These are like ripples behind a rock in a stream. They create waves on the downward side of the mountain. And these create sort of intense turbulence. It can affect planes, or it can trigger the birth of new storms. And then you can have sea and land breezes. And this is done because the temperature, they heat up and cool down faster. So land heats up faster than water during the day. So what does it do? It pulls cool air in from the ocean into land. And then at night, the reverse happens. And it occurs in the Florida Peninsula, etc. So let's wrap this up. So here's a recap. We talked about some of the basic science, and we talked about thermodynamic and hybrid pressure systems. Real quickly on climate change. So the question I asked you at the beginning is, who do you believe? Do you believe the politicians, the Pinocchios of the world, or do you believe the Klein scientists? And hopefully if you looked at this particular presentation, you get a sense of how temperature just interacts and how all these systems are interconnected and how temperature changes, particularly temperature differentials, have a profound impact on the kind of weather we experience, and that's what the Klein scientists are telling us. So what can you do from here on out? We've had the standard list here. I just want to mention this one more time. One of the things you need to do if you believe this is a critical problem, and time is running out, folks, we need to elect officials at every level of government who believe climate change is real, are willing to take urgent action to address the issue, and they need to have the personality type and skill sets that they can work cooperatively with other people around the planet to solve this problem. So thank you very much for your time, and I hope you'll join us for one of our other sessions. Have a great day.